Look up at the night sky on a clear evening and find the moon. It is always there. Predictable. Familiar. So constant a presence in human experience that nearly every civilization in history has built myths around it, calendars from it, religions toward it. Poets have written about it for as long as humans have written anything. Sailors have navigated by it. Farmers have planted by it. Lovers have stood beneath it for 10,000 years. We take it entirely for granted. And that is one of the great failures of human imagination. Because the moon, that quiet silver disk hanging in the darkness above your head, should not exist. By any reasonable calculation of what our solar system ought to look like, Earth should be a moonless planet. The fact that we have a moon at all, and a moon of this particular size, in this particular orbit, with these particular properties, is the result of an event so catastrophically violent and so astronomically improbable that scientists spent most of the 20th century arguing about whether it could even have happened. It did happen. We know that now. And the story of how it happened is the story of the most important collision in the history of our world. A collision that did not just create a satellite, but that built the conditions for everything that would eventually follow. The seasons, the tides, the stable climate, the long, unbroken stretches of geological time in which complex life could slowly, patiently evolve. The moon is not an accident sitting in our sky. The moon is the reason we are here. In the last episode, we followed Earth through its most extreme early phase. The formation of the solar system, the violent accretion of the proto-Earth from countless collisions, the differentiation of the planet's interior into core and mantle and crust. We left the young Earth as a battered, partially molten world, still being bombarded from space, still finding its form, but increasingly recognizable as the body that would eventually become our home. But there was something missing from that picture. No moon. In the early period of Earth's formation, roughly the first 50 to 100 million years after the sun ignited, our planet was alone in its orbit. It had no large companion. The night side of that early Earth, if you could have stood on it without being incinerated by the magma ocean, would have shown a sky full of stars but no dominant satellite. No silver disk rising in the east. No tidal pull strong enough to matter. No gravitational stabilizer holding the planet's axis in check. That moonless Earth was a different world. And it would remain different until the day that something arrived to change it forever. That something had a name. Scientists call it Theia. To understand Theia, you have to understand the chaos of the early solar system. We covered the broad strokes in the previous episode. The protoplanetary disk, the accumulation of dust into pebbles into boulders into planetesimals into planetary embryos. But there is a detail worth dwelling on, because it is directly relevant to the story of the moon's formation. The inner solar system, in those first 100 million years, was not home to just 4 planets. It was home to dozens of planetary embryos, bodies ranging from the size of the moon to the size of Mars, all sharing a relatively narrow band of orbital space around the young sun. These embryos did not all have neatly separated orbits. They crossed each other's paths. They competed for the same material. They were nudged and perturbed by the gravitational influence of the giant planets forming in the outer solar system, particularly Jupiter, which was already by far the most massive body in the solar system outside the sun itself. In this crowded, chaotic environment, a particular planetary embryo formed in roughly the same orbital zone as Proto-Earth. Scientists have named this body Theia, after the Titan goddess of sight and light in Greek mythology, the mother of the goddess of the moon. The name was chosen with poetic intent, because Theia, in the hypothesis that now bears the giant impact name, is the mother of our moon. Theia was not a small rock. Current models suggest it was roughly the size of Mars, perhaps a quarter to a third of Earth's current mass. It was, by any standard, a world in its own right. It had differentiated, just as Earth had, with a dense iron core and a rocky mantle. It had formed from the same raw materials as Earth, the same mix of silicates and metals and volatile compounds inherited from the solar nebula. In some of its chemical properties, it may have been nearly indistinguishable from Proto-Earth itself. For millions of years, Theia coexisted with Proto-Earth in a gravitational configuration that planetary scientists call a Trojan orbit. occupying a stable position either 60 degrees ahead of or 60 degrees behind Earth in its orbit around the Sun, held there by the balance of gravitational forces between the Sun, Earth, and its own mass. Jupiter has Trojan asteroids in precisely this configuration today. The so-called Trojan asteroids that share Jupiter's orbital path, but never approach the planet because they are locked at the stable Lagrange points. Theia was, for a time, Earth's Trojan companion. But Trojan configurations are not stable forever. As the solar system evolved, as Jupiter and Saturn shifted slightly in their orbits, as the remaining debris in the protoplanetary disk was swept up and cleared, as the gravitational landscape of the inner solar system changed, the forces holding Theia in its stable position began to weaken. Slowly, over millions of years, Theia's orbit began to change. It began to drift. Its path became slightly elliptical, then more so. The safe distance that had kept it separated from Proto-Earth began to close. And then, approximately 4.5 billion years ago, roughly 50 to 100 million years after the Sun ignited, Theia's orbit intersected with Earth's. What happened next changed everything. The collision between Theia and Proto-Earth was not a head-on impact. This is one of the most important details in the entire story, and it is often overlooked. A direct, perpendicular collision would have had very different consequences. It would have been more likely to simply merge the two bodies into a single, larger planet, or to shatter both of them into scattered debris that would gradually reassemble over millions of years. Neither outcome produces the moon we actually have. What the current models describe instead is a glancing blow. A collision at a relatively shallow angle, perhaps around 45 degrees from tangential, where Theia struck Proto-Earth not straight on but from the side, at an oblique trajectory. The difference in outcomes between a head-on collision and a glancing one is enormous. In a glancing impact, the kinetic energy is transferred differently. More of the outer material, the mantles and crusts of both bodies, is sheared off and ejected into orbit, while more of the core material is retained within the combined body. The angular momentum of the impact is preserved in the spin of the resulting planet, and in the orbital motion of the ejected debris. And in this particular glancing collision, the results were extraordinary. The force of the impact was staggering. Theia, a body roughly the size of Mars, was traveling at several kilometers per second relative to Proto-Earth when the collision occurred. The kinetic energy released at the moment of contact was equivalent to, and this comparison is genuinely difficult to make meaningful, several billion times the energy released by the most powerful nuclear weapon ever detonated by humans. It was not an explosion in any conventional sense. It was a transformation, a fundamental restructuring of matter at planetary scale. In the first hours after the collision, the outer layers of both Theia and Proto-Earth were vaporized. Not melted. Vaporized, turned from solid and liquid rock directly into superheated rock vapor at temperatures of thousands of degrees. This expanding cloud of rock vapor, along with enormous quantities of molten rock debris, was blasted outward from the collision zone in all directions. Some of this material escaped entirely, flung into deep space by the violence of the impact, lost forever. But most of it did not escape. Most of it entered orbit around the surviving Proto-Earth, which had absorbed Theia's iron core into its own, becoming larger and denser and more massive than before. The cloud of debris that now surrounded Earth was enormous. It formed a thick, hot, glowing disk of rock vapor and molten droplets that extended outward from the planet's surface to distances of tens of thousands of kilometers. And then, remarkably quickly, that disk began to cool. As it cooled, the rock vapor condensed into droplets. The droplets accumulated into clumps. The clumps accumulated into larger bodies. The same accretion process that had built the planets themselves, dust to pebbles to boulders to planetesimals, now repeated itself in miniature, at extraordinary speed, within the debris disk orbiting Earth. Models suggest that the moon formed within this disk in as little as a few decades to perhaps a few centuries. On any geological timescale, this is essentially instantaneous. The debris from the most violent event in Earth's history coalesced into our moon faster than the Roman Empire fell. Within this almost incomprehensibly short window of time, a new world had appeared in Earth's sky. The moon that formed from the Theia debris was not the moon we know today. It was much, much closer. Current models of lunar orbital evolution suggest that immediately after its formation, the moon orbited Earth at a distance of perhaps 15,000 to 20,000 kilometers, roughly 25 times closer than it is today. To put that in perspective, the moon today sits about 384,000 kilometers from Earth on average. The newly formed moon would have been visible in the sky as an object roughly 25 times larger in angular diameter than the moon we see now. It would have filled an enormous arc of the sky, looming vast and overwhelming, its surface still glowing with residual heat from the violence of its formation. And it was not silent in its influence. The gravitational pull that a massive object exerts on a nearby body scales with the inverse square of the distance, meaning that when the moon was 25 times closer, its tidal force on Earth was not 25 times stronger, but approximately 625 times stronger than the tidal force the moon exerts today. Consider what the tides look like today. In certain locations, the Bay of Fundy in Canada, for instance, tidal ranges of 15 or 16 meters are recorded at extreme tides. These are produced by the gravitational pull of the moon at its current distance. Now multiply that force by 600. The early Hadean tides, driven by the newborn moon at close range, would have been tidal bores of extraordinary scale, sweeping across the early coastlines, if coastlines even existed yet, with a violence difficult to imagine. In the global magma ocean that covered proto-Earth in the immediate aftermath of the Theia impact, those tidal stresses did not produce waves. They produced enormous convective stirring of the liquid rock, adding additional heat to the system, maintaining the molten surface for longer than it would otherwise have persisted. The moon was not yet the gentle, serene presence it is today. It was a force of geological violence. How do we actually know any of this? It is a fair question. The Theia impact happened 4.5 billion years ago. No human was there. No instrument recorded it. The geological record of the Hadean Eon on Earth itself has been almost entirely erased by billions of years of plate tectonics, volcanic activity, erosion, and reworking of the crust. So how can scientists speak with any confidence about what happened? The answer comes from multiple lines of evidence that, taken together, build a remarkably coherent picture. The first and most direct evidence comes from the moon itself, specifically from the lunar rocks returned to Earth by the Apollo missions between 1969 and 1972. Those samples, totaling approximately 382 kilograms of material collected from 6 different landing sites, have been analyzed in extraordinary detail in laboratories around the world for more than 5 decades. And one of the most striking findings to emerge from that analysis is the chemical similarity between lunar rocks and Earth's mantle. The key measurement is isotopic ratios. Specifically, the ratios of different isotopes of oxygen, titanium, chromium, and tungsten found in the lunar samples. Different bodies in the solar system have subtly different isotopic fingerprints, reflecting where and when they formed within the protoplanetary disk. If the moon had formed somewhere else in the solar system and been captured by Earth's gravity, one of the pre-Apollo hypotheses for lunar origin, its isotopic signature would be detectably different from Earth's. It is not. The isotopic composition of lunar rocks is, within measurement precision, essentially identical to that of Earth's mantle. The moon and Earth are built from the same material. The most natural explanation for this identity is that the moon was largely assembled from material that was originally part of Earth, blasted off by the Theia impact, and then reaccreted in orbit. The second line of evidence concerns the moon's composition. The moon is anomalously depleted in volatile elements. Substances like water, sodium, potassium, and other compounds that vaporize at relatively modest temperatures. This depletion is consistent with a formation process that involved enormous heat, exactly what you would expect from the vaporization of rock in a giant impact. A moon that had formed through some gentler process, or been captured from elsewhere in the solar system, would not show this pattern of volatile depletion. The third line of evidence is dynamical. It concerns the angular momentum of the Earth-Moon system. The rate at which Earth spins, combined with the orbital motion of the moon, encodes information about the history of the system. When planetary scientists run computer simulations of different scenarios for the moon's origin and compare the resulting angular momentum to what we actually observe, the giant impact scenario is the only one that naturally produces a match. No other hypothesis for lunar origin. Fission, where the moon spun off from a rapidly rotating Earth. Capture, where the moon formed elsewhere and was caught by Earth's gravity. Co-accretion, where the moon formed alongside Earth from the same disk material, successfully accounts for all three lines of evidence simultaneously. The giant impact hypothesis does. This does not mean the story is complete. Far from it. In recent years, increasingly precise isotopic measurements have revealed some tensions in the simple version of the giant impact model. The moon's composition is almost too similar to Earth's mantle, more similar than the original models predicted it should be. Some researchers have proposed modifications. Perhaps Theia was more compositionally similar to Proto-Earth than previously assumed. Perhaps the collision was more energetic than the standard model suggests, more thoroughly mixing the two bodies' material. Perhaps multiple smaller impacts rather than one giant one contributed to the moon's formation. The debate continues. But on the central question, that a giant impact between Proto-Earth and another planetary body was responsible for the moon's formation, the scientific community has reached a broad consensus that has only strengthened over the decades. The consequences of the Theia impact were not limited to the creation of the moon. They extended to virtually every aspect of what Earth would become. Begin with the simplest and most immediately obvious consequence: size. The merger of Proto-Earth and Theia's iron core made our planet significantly larger and more massive than it would have been without the collision. A larger Earth has stronger gravity, which means it can hold on to a thicker atmosphere. A larger Earth has a larger iron core, which means a stronger and longer-lasting magnetic field. Both of these properties proved critically important for the subsequent development of life. Then consider the axial tilt. Before the Theia impact, Proto-Earth's rotational axis was oriented differently than it is today. The exact pre-impact orientation is unknown, but the impact dramatically changed it. The glancing blow of the collision, transferring angular momentum to the combined body, tilted Earth's rotational axis to approximately 23.5 degrees relative to the plane of its orbit around the Sun. That 23.5-degree tilt is the reason Earth has seasons. As Earth orbits the Sun over the course of a year, the tilt means that first the northern hemisphere, then the southern hemisphere, is angled more directly toward the Sun. The half pointed toward the Sun receives more intense sunlight, summer. The half pointed away receives weaker, more oblique sunlight, winter. Without the tilt, there would be no seasons. The equator would be permanently hot, the poles permanently cold, and the temperate zones that host most of Earth's biodiversity would experience a monotonous, unchanging climate through the year. Seasons matter for life in ways that are profound and easy to underestimate. They drive the annual cycles of plant growth and animal behavior. They create periods of stress and abundance that natural selection acts on. They shape migration patterns, reproduction timing, and the extraordinary diversity of biological strategies that living organisms have evolved to cope with changing conditions. The entire seasonal architecture of Earth's biosphere, every spring bloom, every winter dormancy, every migration of birds, traces its existence back to the angle at which Theia struck Proto-Earth 4.5 billion years ago. Then consider the rotation rate. The Theia impact left Earth spinning dramatically faster than it had before. A day in the immediate aftermath of the collision lasted only about 5 or 6 hours. That rapid spin had its own consequences for atmospheric circulation, for ocean dynamics, for the behavior of the magnetic field. Over billions of years, the moon's tidal braking has slowed Earth's rotation to the 24-hour day we know, a process that is still ongoing. The moon continues to recede from Earth at approximately 3.8 centimeters per year, and the day continues to lengthen by tiny, imperceptible fractions of a second per century. But perhaps the most profound long-term consequence of the moon's formation is the one that is least obvious: the stabilization of Earth's axial tilt. The moon is very large relative to Earth, unusually so by the standards of the solar system. Most moons are tiny compared to their parent planet. Our moon is about 1/81st of Earth's mass, which is an extraordinary ratio, and that large mass at its current distance exerts a gravitational torque on Earth's equatorial bulge, the slight flattening of Earth's shape due to its rotation, that acts as a gyroscopic stabilizer. Without the moon's stabilizing influence, Earth's axial tilt would not remain at 23.5 degrees. Computer simulations show that without the moon, Earth's tilt could vary chaotically over millions of years, potentially ranging from nearly 0 degrees to more than 85 degrees. Such extreme variations would produce climate swings of devastating severity. At near-zero tilt, the poles would be in permanent darkness or permanent light, and the seasonal cycles that drive so much of Earth's biology would vanish. At extreme tilts, the poles would receive more solar energy than the equator during summer, producing a climate unlike anything in Earth's recorded history. Mars, which has no large moon, exhibits exactly this behavior. Mars's axial tilt has varied between about 10 and 60 degrees over the past few million years, a range that has contributed to dramatic swings in its climate, including periods when its polar ice caps grew to cover much of the planet. Mars's climate instability is, in part, a consequence of the absence of a large moon. Earth, by contrast, has been remarkably stable in its axial tilt over geological time. The variations have been modest, between roughly 22 and 24.5 degrees, oscillating on timescales of about 41,000 years. This modest oscillation is actually one of the drivers of the ice age cycles that have characterized Earth's recent geological history. The Milankovitch cycles, named after the Serbian astronomer who worked out the mathematics. But these are gentle variations around a stable mean, not the chaotic swings that would occur without the moon. A stable axial tilt means a stable climate regime. And a stable climate regime, maintained over hundreds of millions of years, means that evolution can proceed without being constantly disrupted by catastrophic environmental upheavals. Complex life needs time. It needs stability. It needs millions of generations of relatively consistent conditions in which natural selection can do its patient work. The moon gave Earth that stability, and the moon exists because Theia died. There is a philosophical dimension to this story that is worth sitting with for a moment. The moon's formation was an accident. Theia's orbit did not drift toward Earth's because someone arranged it. Jupiter's gravitational influence did not nudge Theia off course according to any plan. The collision happened because of the blind, deterministic operation of physical law, gravity and orbital mechanics doing what they do, indifferent to outcomes. And yet the outcomes of that accident include the seasons, the tides, the stable climate, and ultimately, through hundreds of millions of years of evolution made possible by that stable climate, every living thing on Earth, including the organisms that eventually became intelligent enough to look up at the moon and wonder where it came from. This is a recurring theme in the story of this planet, and we will encounter it many times as this series progresses. The events that made Earth habitable, that made complex life possible, that set the stage for the eventual emergence of humanity, many of them were not inevitable. They were contingent. They depended on specific collisions, specific orbits, specific timing, specific chemistry. Change any of them, and Earth's history looks very different. The Theia impact is perhaps the most striking example. If Theia's orbit had been slightly different, if it had missed Earth entirely, or struck at a different angle, or been much larger or much smaller, there would be no moon in our sky. And without the moon, Earth would be a different world, possibly still habitable, possibly still host to some form of life, but almost certainly not host to the particular chain of events that led, step by step, to us. We are here, in part, because of an accident that happened 4.5 billion years ago. That is either a humbling thought or a thrilling one, depending on your perspective. Perhaps it is both. In the billions of years since its formation, the moon has been slowly retreating. The mechanism is the same tidal interaction that has slowed Earth's rotation. As Earth rotates beneath the moon, the tidal bulge that the moon raises on Earth's oceans is carried slightly ahead of the moon's position by Earth's rotation. The gravitational interaction between that displaced bulge and the moon transfers angular momentum from Earth's spin to the moon's orbit, ever so slightly accelerating the moon's orbital speed, which causes its orbit to expand. The moon drifts outward. Earth's rotation slows down. Both effects are tiny on any human timescale, but over billions of years they add up to something significant. When the moon first formed, it was perhaps 15,000 to 20,000 kilometers away. Today it is 384,000 kilometers away. The moon has been moving outward for 4.5 billion years, at an average rate that has varied over time, but works out to a few centimeters per year. And because the moon is now much farther away, it appears much smaller in the sky than it once did. But here is something remarkable. At its current distance, the moon appears almost exactly the same size in the sky as the sun. The sun is about 400 times larger in diameter than the moon, but it is also about 400 times farther away, which means their apparent sizes very nearly cancel out. This is why total solar eclipses are possible. When the moon passes directly between Earth and the sun, it covers the solar disk almost perfectly, not too large, not too small. This is, of course, a coincidence. The moon's current distance from Earth is not specially arranged. It is the result of 4.5 billion years of gradual recession, and it is a temporary coincidence. In the distant future, as the moon continues to move outward, it will appear smaller than the sun, and total solar eclipses will no longer be possible. In the deep past, when the moon was much closer, it would have covered the sun completely, and the eclipse would not have revealed the solar corona in the way that makes modern total eclipses so visually stunning. We happen to live at the particular moment in Earth's history when the moon is exactly the right distance to produce perfect total solar eclipses. Ancient humans who witnessed these events had no way of knowing they were observing a cosmic coincidence, that they were alive at precisely the right era in geological time for this particular piece of celestial geometry to work out. But we know. And it is one more reminder that the story of Earth and Moon is full of contingencies that, taken together, add up to something that feels almost impossibly fine-tuned. Not because it was designed, but because we are the survivors. We are the product of the version of history where everything worked out. All the other versions, the ones where Theia missed or the moon never formed or the axial tilt went chaotic, those do not have observers to tell their story. We are here because this version of events happened. And this version of events is the story we are telling. The moon's formation marks the end of the most violent phase of Earth's early history. The Theia impact was the last truly planetary-scale collision that Earth would endure. After it, the planet that emerged, larger, tilted at 23.5 degrees, spinning fast, with a new satellite glowing enormous in its sky, began the long, slow process of cooling and settling and becoming, over billions of years, the world we know. But cooling and settling does not mean peaceful. The Hadean Eon that followed was still a hellscape by any modern standard. The surface was still largely molten. The atmosphere was still toxic. The bombardment from space, though less intense than during the period of planetary accretion, had not stopped. And the moon itself, in its first billion years, was subjected to the same bombardment. The impact craters preserved on its surface today are the scars of that era, frozen in the lunar rock because the moon, unlike Earth, has no plate tectonics or erosion to erase them. Those scars are a record, a geological diary of the early solar system that Earth itself has largely lost. In the next episode, we turn our attention to what came next. A transformation so profound that it reshaped not just Earth's surface, but its entire relationship with the universe. The first permanent oceans, the first stable chemistry, the first hints, buried in the chemistry of ancient rock, that something new and extraordinary was stirring in the depths of those early seas. Earth has survived its greatest collision. The moon hangs in the sky. The planet is scarred but intact. The stage is set. And in the darkness of the first deep ocean, the most improbable story in the known history of the universe is about to begin. Before we move forward, there is one more dimension of the moon story worth exploring, because it connects the cosmic violence of the Theia impact to something that feels surprisingly intimate. The tides. We experience tides today as a modest rise and fall of sea level. A few meters at most in most coastal locations, more in certain geographically amplified settings. They are predictable, rhythmic, useful for sailors and fishermen and coastal engineers. They are a background feature of life on the coast, noticed and then forgotten, like the weather. But the tides are not merely a coastal convenience. They are one of the most important forces that have shaped life on Earth. And their story begins with the moon. When the moon was first formed, so close and so massive in the sky, the tides it raised were of extraordinary scale. Across the global magma ocean of the early Hadean Earth, tidal forces hundreds of times stronger than today's stirred the liquid rock in enormous convective currents. The tidal heating this generated helped maintain the magma ocean in its molten state, delaying the formation of a stable solid crust. In the most violent early phase, the moon and Earth were locked in a relationship of mutual gravitational torment. The moon's gravity stirring Earth's molten interior, Earth's gravity gradually reshaping the moon's orbit. As the surface cooled and the first oceans formed, the tides shifted from stirring magma to stirring water, and the consequences for life were profound. Tides create intertidal zones, the strips of coastline that are submerged at high tide and exposed at low tide. These are some of the most biologically productive and dynamically interesting environments on Earth. They are transition zones between ocean and land, between wet and dry, between salt water and fresh, between submersion and exposure to sunlight and air. The organisms that first colonized intertidal zones, hundreds of millions of years from now in our story, face precisely the kinds of challenges that drive evolutionary innovation. The need to survive drying out, to withstand temperature fluctuations, to anchor themselves against the tidal currents, to exploit resources that no purely marine organism could access. Many scientists believe that the tidal zone played a crucial role in the eventual colonization of land by life. That the rhythm of the tides, cycling organisms between aquatic and aerial environments twice a day, was one of the pressures that drove the evolution of the adaptations that eventually allowed life to leave the ocean entirely. Without strong tides, there is no strong tidal zone. Without a strong tidal zone, the transition from ocean to land may have been harder, slower, or taken a different form entirely. The moon made the tides. The tides shaped the coastlines. The coastlines, over hundreds of millions of years, shaped the organisms that lived in them. And those organisms eventually gave rise to land life, and to the chain of evolution that produced, among much else, us. The Theia impact. The formation of the moon. The tidal forces of a close satellite. The intertidal zone. The colonization of land. The evolution of land vertebrates. Mammals. Primates. Humans. Every link in that chain is connected. And the first link was forged 5 billion years ago, in the most violent collision this planet has ever experienced. There is another consequence of the moon's formation that rarely receives the attention it deserves: its effect on Earth's volcanic and geological activity. The tidal heating produced by the moon's gravitational pull in the early Hadean did not just stir the magma ocean. It generated additional thermal energy within Earth's interior. Energy that contributed to the prolonged geological activity of the planet's early history. Some researchers have proposed that the moon's tidal influence may have played a role in triggering or sustaining early plate tectonics, the system of moving crustal plates that has been one of the defining features of Earth's geological history for at least 3 billion years. Plate tectonics is, in ways that are still being worked out, one of the prerequisites for complex life on Earth. It cycles carbon between the surface and the interior of the planet, drawing carbon dioxide out of the atmosphere through the weathering of silicate rocks, depositing it on the ocean floor as carbonate sediment, and eventually subducting it back into the mantle through the movement of tectonic plates, where it is released again by volcanic activity. This carbon cycle acts as a long-term thermostat for Earth's climate, preventing the runaway greenhouse effect that has made Venus permanently uninhabitable, and preventing the permanent global glaciation that would occur if the carbon cycle stopped drawing carbon into the oceans. Without plate tectonics, Earth's climate over geological timescales might have been far less stable. Without the moon's tidal contribution to the heat budget of the early Earth, plate tectonics might have started differently, or later, or not at all. The connections are speculative, and the details are still being worked out by geophysicists and planetary scientists. But the general principle is becoming clearer. The moon is not merely a passive presence in the night sky. It is an active participant in Earth's geological and climatic history. its formation, its proximity, its gravitational influence. All of these have shaped the planet in ways that extend far beyond the obvious effects of tides and eclipses. The Moon is not just Earth's satellite. It is Earth's partner. The two bodies have been influencing each other continuously for 4.5 billion years, and that mutual influence has been one of the threads running through all of Earth's subsequent history. One final thought before we close this chapter of the story. Among all the planets and moons in our solar system, the Earth-Moon relationship is unusual in a way that becomes more striking the more you think about it. Mars has two moons, Phobos and Deimos, but they are tiny irregular bodies, almost certainly captured asteroids rather than products of a giant impact. They are so small that their gravitational effect on Mars is negligible. Venus has no moon at all. Mercury has no moon. The outer gas giants have large moons, but those moons are small relative to the mass of their parent planets, and they form through different processes, primarily accretion from the circumplanetary disks of gas and dust that surrounded the giant planets as they formed. Among the terrestrial planets, the rocky inner planets, Earth is unique in having a large, geodynamically significant moon. A moon so large relative to its parent planet that some scientists have described the Earth-Moon system not as a planet with a satellite, but as a double planet. Two worlds orbiting a common center of gravity that happens to lie inside the larger of the two bodies. This uniqueness is directly relevant to Earth's habitability. The Moon's size and proximity, the tidal forces it exerts, the axial stabilization it provides, the geological consequences of its tidal heating. All of these are functions of its size relative to Earth. A smaller moon would not stabilize the axis as effectively. A moon farther away would not drive tides of sufficient scale to shape intertidal zones. The specific properties of the moon, its size, its distance, its composition, are the products of the specific properties of the Theia impact. Different impact, different moon, different Earth. We could ask, how common are giant impacts? How likely is it, around any given sun-like star, that a terrestrial planet will experience a Theia-scale collision that produces a large moon? The answer is that we do not fully know. Giant impacts appear to have been common in the early solar system. The geological evidence from multiple bodies suggests that large collisions were a normal part of the accretion process. But Theia-scale impacts that produce planet-sized moons rather than simply merging the colliding bodies may require a specific and somewhat lucky combination of impact angle, relative mass, and impact velocity. As we discover more and more exoplanets, planets around other stars, one of the questions researchers are beginning to grapple with is how many of them might have large moons. The answer matters enormously for the question of how common habitable planets are in the universe. If a large moon is a prerequisite for the kind of long-term climatic stability that complex life requires, and if large moons are rare, then complex life may be rarer than the optimistic estimates suggest. Or perhaps life finds other ways. Perhaps there are forms of complex, even intelligent life that have arisen on moonless worlds, under chaotic axial variations, in climates that shift dramatically over geological time. Perhaps life is more resilient and adaptable than we imagine. We do not know. We have, as yet, exactly one example to work from. This world, with this moon, producing this particular history. And that history, the story of how this planet and its companion went from a cloud of debris orbiting a newborn star to the world capable of supporting everything that came next, is a story whose next chapter begins in the water. The oceans are forming. The chemistry is beginning. Something is stirring in the dark. That is the story we tell next.